So if you recall what we have been discussing, shear strength chapter, right? So in shear strength, we have learned how to draw a Mohr circle. Okay, it is full of Mohr circle only. Okay, and it is very simple. It may look complicated to you, but it is very simple. One reading is enough. So what we are doing is we have these principal stresses, okay, and normal and shear stresses we are plotting for a different soil, maybe normally consolidated clay or consolidated clay, pure sand, and like that we have drawing, and where it touches the number of more circle we have drawn, and we can find out the failure envelope, and from that we can get it the C and the phi parameter, which can be used for our bearing capacity equations. Okay, that we'll see in the next semester. Why this C and the intercept C and the phi parameters are important. Okay, so those are the shear strength parameter. So hope you have started reading this one. Okay, particular chapter. Okay, so and we have seen some different tests. Okay, whether we have covered this Windshear test. Please respond. Whether we have covered this Windshear test. Hope you are listening. No idea, right? Please respond. Someone should respond. Divya. Class step.
Sir?
Whether we are aware whether we have covered this or not. You are not aware, right? So anyway, you are not aware, and
we have studied up to only triaxial compression.
yeah, triaxial, I think. Okay. Anyway, fine. So triaxial. Anyway, I will explain those things also. What we have done previously in the triaxial test. Okay. Again, we will recall it. I have shown some videos also, right? Triaxial. If you
Yes, sir.
yeah.
Yes.
So triaxial test, what we are doing is we are applying the all over stresses, that is sigma 3. Okay, principal stress, and on the top sigma 3 plus one more stress, that is deviator stress, that would be sigma 1. Okay, sigma 2 we are neglecting here. Sigma maximum principal stress and minor principal stress we are applying it. Okay, so like that we can we have seen different drainage conditions, right? So we have seen unconfined compression test also we have seen, undrained, and the UU test. Okay, unconsolidated undrained test, and unconsolidated drain test, and consolidated drain test, CD test, and so on. Quick test, medium test, and the long-term test, and so on. Okay, so this triangle test is more controlled over, and we have seen the direct shear test also. Simply we are what do you say, shearing the soil sample by using box shear. From that, when you draw a plot, you will get C and phi parameters. Okay, here also we can draw the Mohr circle, and on the when you draw the failure envelope with the tangent, you will get the C and the phi parameters. Okay, so these are one reading is enough. Okay, there is nothing, so no need to confuse. Okay, so only thing you have to read every day whenever I am teaching it. Okay, once again, if you read after 1 month, you may not be remember anything. So every day reading is must. So this Windshear test is again, this test is used for again finding the shear strength of the soil. Okay, especially shear strength for a cohesive soil, we will get it from the cohesion only, C parameter only. Okay, here we are not talking about the angle of internal friction phi. So to find the shear strength, we use this Windshear test. Okay, as the name suggests, so we'll be having few vents here, and here we are applying the torque, rotating it. Okay, and what happens after soil fails? Okay, So what happened? This reading it shows. Please.
So your screen is not visible.
Screen is not visible, right? Sorry. Good that at least you are responding. Want to see screen. Okay. Anyway, so this is the Windshear test. Okay. So here, anyway, I will show some video. Then only you will understand better, because in online class, no, we have this privilege to show some videos so that you can further understand this particular. As the name suggests, some vanes would be there. Okay, here we apply torque T, and from that torque, okay. So this derivation, anyway, this derivation also I can explain you. So what we are doing is here. The derivation, in the derivation of the formula, what we'll do is first you see this particular Windshear test, then only we can go ahead with this one. Let me check we have any videos for this Windshear test. Laboratory, right? We can have in the field also this particular Windshear test. Let us check this one, okay?
So we have determined the shear strength of a fine clay to which we test the vein shear test of a
So this is the apparatus, okay?
So
Here this is the vein.
for vein shear test is this is vein of this vein shear instrument.
So this is the vein, okay? Here what we'll do is in this particular soil would be kept, and this particular Windshear test would be used for clay soil only, okay, not any other soil. So what happens here, we have drum to applying this particular torque, okay. When this two needle would be there, okay, here, when these two needles separates, we say that the soil fails, okay. Anyway, I don't know how is he explaining, but let us see.
This is the specimen holder or specimen container. The dimension of the specimen container is 37.5 mm diameter and 75 mm height. This is the soil. We have passed through 600 micron sieve and add a water of 30% and mix with properly. So now we have to prepare the sand. 30%.
Anyway, this we will do in our unit class, okay. How this test.
Like that. And the top position should be smoothened like that. Sample for vein shear test is prepared. Now it has been placed in the vein shear apparatus. Now the soil specimen.
This is the vein, okay. This is the vein, whatever we see it. Here they will keep sample and they will rotate it.
Are placed like that in this vein shear apparatus. This is the needle for vein and this is a vein, 90-degree vein.
We have
we
four
have
veins.
to move up the vein by rotating this handle. We move up the vein upward. And now we have to place the weight of that sample like that. The penetration of this vein should be 10 mm from its top position. And firstly, we have to take care that the reading should be zero. This is the circle. The reading should be zero like that, and we have to penetrate the vein. Now we have to penetrate the vein. The vein is penetrated, and the penetration should be surface. Firstly, we have to the spring. We have to attach like this. We have to rotate the vein a rate of 0.1 degree per second like that, like this. This is the handle for providing a torque to this vein like that. Like that, the we have to apply the torque until the soil fails. We should look into this soil sample. We have to take a reading.
So that's what this some procedure. Okay, when this so this is designed such a way that we can easily find out when the soil is fails. Okay, so this is all about the Windshear test. Anyway, you'll do it for in geotechnical laboratory. Okay, you have to prepare a soil sample, and only thing is we are applying a torque that you should remember. Okay, and we are finding the where the soil fails. Okay, here if you see this formula, anyway we'll check it what it is exactly. Okay, so derivation of the formula, in the derivation of the formula it is assumed that the shear strength S of the soil is constant. Okay, in the, all along this shear, then the torque applied T must be equal to sum of the resisting torque at the sides T1 and that at the top. Okay, bottom and the top. That means we have these veins top and the bottom, right? So that's what it is showing. The resisting top on the side is equal to the resisting develop along the cylinder. Okay, so this is like we have a cylinder of this is H. Okay, and this is the diameter. Like our engineering mechanics formula, we can write it as okay, torque T1. What is this T1? 1 minute. So this is like pi d h, okay, pi d h, and with what are the T1 and T2? Here T1 is resisting torque at the sides T1, and the T2 the top torque T2. Okay, so the resisting torque and sides also will be there. Hope you are visualizing. Okay, this is the vein. This is the vein. This is the top view of vein. So there is side resisting here, this side. It is like a circle, right? Whole circle. And this would be sides. And there would be top and the bottom here. Here and the here. So this is the side. Understand? This is the side and this is the top and the bottom. Okay, that's what it is given. Like for this, we can take a circle and we can take a small strip like our engineering mechanics we have done. Okay, and with the dr, the resisting torque T2 due to the resisting torque, what they have given is 2 pi r 0 to d by 2. They have done it. Okay, and slowly, what you will get it. This simple thing only. Okay, you will get shear strength S from here. That means you will get this formula. Here, once we know the torque, T, this we know anyway, whatever we applied, okay. And once you know the diameter, okay, once you know the height, we can get the shear strength. That's what it is given, okay. So remember this formula because they will ask in so many competitive exams, okay, when you write it, they will give torque, they will give diameter, and they will give height, and you can get it this particular shear strength. Here, what is shear strength here? Shear strength nothing but the cohesion only, C only. The shear strength of the soil under the undrained condition is equal to apparent cohesion Cu only, because there is no term like Ce, phi term is not there. Okay, so phi term is not there. So here only we have C term only. So remember that by using Windshear test, you will get only C value. That is cohesive soil only. We generally do it. So what are the merits and the demerits of this Windshear test? The test is simple and quick. It is ideally suited for a determination of the in situ undrained shear strength of a non-fissured, fully saturated clay, if possible. Okay, a test can be conveniently used for sensitive soil also. What are the demerits? It cannot be conducted on a fissured clay. That means soil which is having already failure planes. Okay, or a clay containing a sand. Okay, because we cannot do it because these veins will break it for if we use the sandy soil. Okay, so we cannot use for sand or silt soil. We only use for soft clay. Understand? Uh, this test does not give accurate result when the failure panel is horizontal. Okay, that means fissured clay generally we will not use it. So we use it for clay soil, that you should remember, and we will apply the torque. Okay, how to find that equation is given. How we have to find out is whatever resisting torque is there all along the side and the top and the bottom, and likewise we can find out the torque. Okay, so that's what it is given here. And one more important topic in this particular uh, chapter is quicksand condition. Sorry, liquefaction. So this particular chapter is full of more circle only for different soil they have drawn it. Okay, so one more important topic is liquefaction of the sand. Is it visible?
Yes, sir.
Yeah. Even Windshear test also you can see some of the videos here. So I will put it some of the videos. Even if you have doubts, something like this. Okay, so this kind of videos also you can see it. People are giving so how to derive this one. Okay, so this is very simple. Maybe resisting torque L along the top, if you do it and add it, you will get this T value. Okay, so now we will focus on this uh, liquefaction of a sand. This is very important actually. They will ask in all competitive exams what is this liquefaction of a sand is all about. So here what is happening is uh, the sand loses its strength. Okay, when earthquake happens, uh, the pore water pressure develops at the bottom of the soil. Okay, when the pore water pressure develops, liquefaction, the shear strength becomes zero. Understand? So this is the phenomena where the shear strength becomes the zero. So we know that what is the equation for the shear strength. We know that C equals S equal to C plus sigma tan phi. This equation we know here. This equation, anyway, we know this equation. Okay. So here S is called, earlier we have discussed, S is called C plus sigma tan phi. Here C we are taking 0 because this liquefaction takes place in a sandy soil only, because there won't be any liquefaction in the shear, because it is difficult to become shear strength becomes 0 in clay soil, because clay soil will have some cohesion. Okay, but in the sandy soil, this particular liquefaction takes place generally in the loose and fine sand. Okay, which is having equal wide ratio, equal size of the particles. So what happens? There are so many studies you could see on the liquefaction. Even people have worked out so many PhD degrees they have done on the liquefaction. Okay, so whenever earthquake happens, right? So bottom of the earth, if it is a loose sandy soil, okay, and which is having a water table, because of that water table is rises, okay. So what happens, the water table, the pore water pressure increases. When the pore water pressure increases, the stress, the effective stress become 0. It may be equal to effective stress, okay. And with that, what happens, whole stress strength of the soil becomes 0. That's what it is given here, okay. Here what it is given is, if the sand deposit is at a depth of Z below the ground and the water table is at a ground surface, okay, the effective stress we can calculate, okay, gamma saturated minus gamma WE. This one we know that. Here we can write in this way, okay, S is equal gamma dash Z at a depth Z we are taking here, okay, and tan phi. Here what happens, if the pore water pressure, this minus U dash, okay, we call it as a minus U dash. If the sand deposit taken into earthquake or any other oscillation, extra pore water pressure develops, okay, and shear strength equation become this. Hope you are following, okay. From this to the equation become like this. Anyway, then what happens, this where the pore water pressure will go, we have to include in the equation, right? So already we know that, or you can take this as a total stress. Okay, sigma is the total stress and mu is the effective pore water pressure, okay. So whole effective stress, then if this mu becomes this one, gamma into Z, then what happens, this whole equation becomes 0. Then what happens, shear strength loses its strength, okay. Soil loses its strength. So what we are doing here is, by this equation we will see that the by making this S become 0, okay, gamma dash Z minus gamma WH is equal to 0. When you make it 0, then what you will get, ultimate equation is H by Z is the gradient, okay, and this gamma dash by gamma W, okay. What is gamma dash? We know this equation, G minus 1 gamma W 1 plus C, and finally you will get this equation. This is called the critical gradient. So this particular equation they will ask in the GATE and other exams, okay. They say that they will give the Z value, they will give the E value, they will ask us to find out the what is the critical hydraulic gradient with which this liquefaction takes place. Then what we have to do, we have to use this equation, G minus 1 by 1 plus E. You have to get this critical hydraulic gradient for formation of the liquefaction. Understand? Now I will show you in the videos how this liquefaction takes place, okay. So many buildings in the world collapse because of this liquefaction of the sand. So many buildings, hundreds of buildings, whenever earthquake takes place in California, any other some desert areas, or where and many places, okay, seashore places where liquefaction takes place. Ultimately what happens, the soil, the complete building is going to sink, will sink, okay, fully sunk already, okay. So likewise you could see so many cases in soil mechanics where the liquefaction takes place. In this particular chapter deals with the few things you should remember by the in this chapter. One thing is, first what we have done is, first we have taken this principal stress concept, okay. So we say that in a soil there are so many stresses, but three stresses we have, which are principal stresses, like strength of material, okay. So again what we have done is, we have conducted a direct shear test where we can find out the where the failure envelope is predefined, okay, horizontal only. Then what we have done is, we started drawing the Mohr circle. By knowing the normal and the shear stresses, we can plot the different Mohr circle, different for the different soil and all. And what we have done is we have joined the tangent of that particular Mohr circle, and we found the C and the phi parameter. C is the intercept in the y axis. Okay, toe, the shear y axis. X axis is normal stresses. Okay, and angle C and phi angle. Why we are finding this one? Because this C and phi are the shear strength parameters which would be used in a bearing capacity equations when you design a foundations. Okay, and what we have seen the how to find out the C5 parameter in a soil by using triaxial test. That what is this triaxial test? We are, whatever happens in the field, same thing we are controlling there in the laboratory. That means suppose the soil is fully saturated in the field, we are saturated in the soil is undrained. Okay, unconsolidated, we are doing unconsolidated here. So the soil is consolidated, we are doing consolidation, and we are checking the parameters. We are plotting the graphs. Okay, more circle, and we are seeing it. That means that is we have three tests, like, right? UU test, CU test, and CD test. Consolidated drain test. Okay, unconsolidated drain test and unconsolidated undrained test. So this water, by using that one we can measure the pore water pressure also. Okay, and one more test is unconfined compression test. There sigma 3 becomes what do you say, 0. Okay, directly you will get the cohesion value. Okay, after that what we have seen? We have seen the Windshear test. Here what is doing in Windshear test? We are applying a torque. We are rotating it by using the vanes. Okay, then what happens? Because of these vanes will try to shear the soil, and by using laboratory equipment we can find out where the soil is sheared. Once you know torque, because we are applying it, input is torque, we are applying the torque. Once you know the torque, once you know the diameter and the height of these vanes, okay, we can easily find out the shear strength S. Okay, so what is our aim in this particular chapter is to find the shear strength S or the shear parameters like C and the phi parameters. Okay, that's the main aim of this particular chapter. Understand? We are drawing the Mohr circle, we are finding the C and the phi parameter, and directly by using the Windshear test also, we are finding the shear. Even we have Windshear test in the not only in the laboratory, we can have in the field also. That I will show you. Field also, yeah, this you can see it some.
This is Windshear test.
And nowadays it has come automatic. Okay, directly you can measure torque and other things. Okay, so
We use it for soft material like soft clay. The way it works is we we insert blades inside the soil until here, and then we turn this Windshear apparatus and see how much strength the soil has. We use scale. The scale is given here in kPa. And then we look at the results and analyze them. I'll do Windshear test on this soft soil.
So he himself prepared the soft soil.
Put Windshear apparatus in the soil.
We can put half.
So that blades are
also, okay,
covered with soil. We make sure that the scale is set to 0. And then we slowly rotate 1 revolution per minute.
It is not directly connected, it will not rotate. We are applying this torque slowly.
There is no more resistance of soil, and we'll check the results. We'll look at the scale. It says 12 kPa. It shows the strength of the soil equal to 12 kPa.
It is directly appreciation, okay. So here this particular guy is having it is directly kPa it is given, but what we are doing here is we are calculating with the torque. By using torque we are calculating, okay. So yes, here directly he is getting in kPa the shear strength. So likewise, modern equipments are there to find out the shear strength of a soil, Windshear test. This particular veins we can press fully. If you press half shear strength, you will get it. That in that case, h by 2 we have to take it. Understand? Height we have to take h by 2. Then it will give the half shear, whatever shear strength you have it. We can insert full also. Okay. That means both the side we can put it. Top and the bottom also can be sheared. Or we can keep the half the Windshear test also. Okay. So now we are focusing on this particular liquefaction, right? So here also I want to show you some videos so that you will understand what it is this particular liquefaction is all about. Okay. So is it visible? Visible?
Yes, sir.
Yeah, but other derivation you can go ahead. There is no problem. Only thing is you have to. I just want to show it because this is very important topic, liquefaction. So even I thought of doing PhD on this particular liquefaction. Okay, but I have chosen file questions. So likewise, the building will. Here they have used a small shake table. Okay, so this particular shake table will try to shake in like an earthquake, right? Earthquake will try to shake it, and these are all the buildings. Now what is happening is the building is already standing actually, but now it is sinking because of this dynamic load, cyclic load, or you call it as earthquake load. Pore pressure develops and the water will try to come up, and this is mostly happening in standing. Very interesting. Because of the pore water pressure, what is happening is more surface is shifting and touching the failure envelope. When touches, soil try to collapse. This pore pressure is increasing, but the pore pressure is increasing. Here, this kind of test we can do in our laboratory also. Okay. Now, happily standing buildings become here this table is moving, okay, shake table is moving, amplitude and the frequency. That's all. It's very important phenomena. Maybe one more, if anything, just I will show this one. Let us see. This liquefaction happens in soil, sandy soil only, okay? We can shake it or drop it, something can be done. Okay. That's how building collapse. Okay. So whole building sinks. So what is happening here? Pore pressure is dominating. Is the mu is dominating and becoming equal to effective stress, and the whole shear strength becomes zero. Okay, that's what the liquefaction and yeah, so many videos are there. Even this derivation also videos are there. Okay, so it is very simple. Only you can go ahead with that to save time. People are explaining very nicely about it. Okay, some of the videos you can watch.
Are you
So with that, today I'll stop. Uh, Let me check it. What are the things left in the our. So when is our exam? I think I have postponed the assignment date. Okay. So when is your exam? 14th, right?